Okay, so hi everyone. Today we will discuss CLIP. This is a model by OpenAI. It was, in their perspective, it was a milestone. When I say milestone, if you go on OpenAI, there are some tags they put to different publications. This is a milestone, meaning it impacts the industry, the world, with these new capabilities. So overall, what CLIP is about? CLIP provides us with the capability of having the two different modalities, for example, of image and text, to sort of speak the same language. When we say speak the same language, that means, if we go technical, it means that they are in the same latent space, their embedding vectors can be compared for similarities, etc. So overall, this specific topic is relevant for both of the courses of Build Your Own LLM and also for the deep learning for computer vision, because it's exactly the bridge between these two domains. Okay, so overall, we'll have the overview about it, understand the architecture, objective, etc., discuss some zero-shot demos it has, and the implications. Okay, so there are two sections here, right? One if someone comes from the aspect of the computer vision, one if someone comes from the aspect of the LLMs. So for the aspect of the computer vision, so prior to CLIP, vision is a closed set discipline, right? So you used to pick a data set, you picked your 1,000 labels, and the model, it could only see those classes. Now, CLIP broke that wall, meaning at inference time, you can ask, is this a man? Is this a plane? Is this a photo of some robot? And you could do that without retraining it, okay? So that's why every text conditioned generation model and every open vocabulary detector built since 2021 either uses CLIP weight directly or copies the recipe, meaning the essence of CLIP itself. Now, for the LLM students, so we all know that we have the transformer, 12 layers, 512 dimensions, etc. Whichever number of parameters, so whichever basically small GPTs that we have, but with CLIP, we have something called the contrastive objective, and it trains differently from an LLM. Instead of predicting the next token, so what happens there, it needs to make the end of sentence. It's this EOS. When you're training models, overall, eventually it needs to know also when something ended, right? Because the length of text is dynamic. So instead of predicting the next token, it needs to make the prediction regarding the end of sentence embedding, and to make sure that it aligns with the image embedding. Now, and again, remember why. When someone gives you as an input an image, okay, so an image, you have width, height, and how many channels. But when someone gives you text, text is of a different length. Okay, so that's why this is something that you need to also take care of course. So the consequence of that is that CLIP's the text encoder, it produces a sentence level vector, which is semantically grounded in the visual concepts, okay? So this is something different from from something which is autoregressive that a large language model learns. Okay, so that's it about that. So like we said, so overall we have this bridge between these two modalities. Any questions before we proceed? Okay. And as you can see overall, I mean, this is an ancestor of many of the modern models. The technique that it has to bridge these modalities. That's why it's considered a milestone in OpenAI perspective, and everyone agrees with it. Okay, so in the first three sections, they are the lecture part. You will know here what CLIP is, why it works. The last two are the what aspect of it, of what doors did it open, and what should you remember when you read modern multimodal papers. So why CLIP exists? So if we look at two aspects, closed vocabulary problem and the labels are expensive problem. So the closed vocabulary problem, when you had ImageNet or whichever, so the things it could identify is only the classes it was trained on. So overall, when you want to introduce a new class, usually you needed to add this additional neuron. You usually used to do transfer learning, you freeze the weights, and then you train it basically for that specific neuron. Plus, it doesn't have the aspect of saying, hey, this is a photo of a cat in a basket, because if you had labels, so what it knows to identify the objects, maybe location, bounding box, whatever, and the label could have been a cat. So to learn things outside of the label is brittle in this aspect. And to transfer this to a new task requires to have a new label data. Okay, we needed to do the annotations. So this is the issue with the closed vocabulary, that the images might have contained a lot more information of the world, but of course, not everything was annotated. It was annotated for the specific classes. Okay, now label cost. And again, the price of labeling, if we can put it that way, changes during the years. So, and today, a lot of it also we generate, right? We simulate, everything depends on the domain that we look at. But overall, if we look at ImageNet took approximately 25,000 people to label 14 million images. So yes, it is expensive, it is slow, and everyone can be happy that we don't need to take care of annotating large data sets. And of course, you have for the specialist domains, so for specific domains, you also need experts, because not everyone can now label information of CT, MRI, ultrasound. You need to be a specialist. And this makes it more complicated, because if you own some company, you want to develop some product, you want to train on some data that you don't have, you need specialist people, etc. So you understand the challenges or the statement of why labels are expensive. Now, of course, across the web, we have endless amount of data, images, captions, and the captions describe the image. So this is a very good start if this is information that we can leverage. Any questions so far? Okay. Now, one thing to remember about CLIP. So CLIP doesn't look at this just as a label. It looks at this as it's an actual caption that a human wrote. And then overall, if we look at that data, that we have across the web. So now all of a sudden we have larger amounts of data that we can use for training our models. So the ideas that made CLIP work, basically. So it's the aspect of natural language supervision. So you do use the raw caption as the target instead of the label. So we have an image of a cat. We don't just take the label of a cat. And now we also have the vocabulary of phrases. This is not 1,000 indexes. And what it means, this is not an array of predefined labels that we identify. So this is number one. Number two, this is also novel overall. So they scraped 400 million image and the text. They took it from the public web. So it's 30 times more data than whichever other data sets, etc. So they scraped the data quite easily versus ImageNet, the work that needed to be done there with the 20,000 people and 14 billion images. So here they have more data. They needed to do less work in order to have it. This is additional benefit. Okay, now the third component is the actual contribution. So this is about the contrastive aspect of it. So the original CLIP authors, they first tried to predict the exact caption tokens. Now, back then they had like a 63 million parameter transformer. So this approach was like 3 times slower than just predicting which one of a 32 candidate caption it matches. So what they did, they switched to a contrastive object, and this one scaled. So in their paper, they said it was 4 times more efficient versus the generative baseline at the same compute. Okay, so this is one of the most cited aspects in modern multimodal machine learning. Okay, so overall, it's useful, it's generalizable, and because now you have rich data, and because of the prediction space is enormous, right? I mean, the prediction space, it's not just labels that someone labeled in ImageNet. So that space is much bigger. So for those cases, the constructive objectives, they often outperform the generative ones. Because they only ask the model to discriminate, it shouldn't reconstruct. Okay, and remember, it's given a selection, let's say from 32 options, which is which. Okay, any questions so far? Okay, let's proceed. So the building blocks, everything that you need to know in order to read the CLIP paper. Okay, so embeddings. So one of the important aspects in the lecture overall is that embedding is basically the mappings that we learn from the raw inputs that we have. If it's an image, so it's pixels. If it's text, it's characters or tokens, whatever, or audio samples, whichever modality we have. So it takes it, it maps it to a fixed length vector in some dimension that we define. And of course, there is no magic number. It's always aspects of experimentation and running the different experiments, different sizes to see the ideal scores that we get. Now, the vectors, they are meaningful only because of the training objectives that shape them. So if you train it with something called the triplet loss, if you do it that way, then similar things end up closer. And if you train with the reconstruction loss, then it's geometry. It encodes basically a statement of whatever is needed to reconstruct. So if you train with something called cross entropy on classes, then the geometry is the one that separates classes. By the way, afterwards, I will share some interactive examples that we can look at. So overall, given that we have the embedding, we have the aspect of the mapping, and like we said, if you do it with the triplet loss, then similar things ideally map to similar vectors in the aspect of what's the similarity of them. Usually distance is cosine similarity, and dimension, of course, changes, but CLIP uses 512. And of course, 512 is smaller than the raw input, because if you look at an image and an image is high definition, so high definition is like 2 million pixels, right? It's 1920 by 1080 by number of channels, which is usually 3, sometimes 4. Okay, so it's not only the architecture, right? It's also the aspect of how we train it. And there, for example, the triplet loss function is crucial for that. Okay, so if we look at the code here, so in this example, of course, checking if we have the CUDA device, loading the visual transformer here, so you have the model and the preprocessor. You take an image, pass it through the preprocessor, upload to the device, you have the image. And once the image is on the device, which is the GPU, you are doing the encoding of the image, then you're getting the image embedding. And then you want to embed a sentence, so you take as an example, let's say we want to tokenize a photo of a cat. We are encoding that text. And then we want to do the comparison. So we take the image embedding, we divide by the normalized form, same we do for the text, and then we compute the aspect of the cost similarity. And if the image is an image of a cat, then the similarity score is ideally high, up to 1. And if it's not an image of a cat, and the model was trained correctly, and it's capable of that, then ideally the score should be close to 0 to differentiate between correct answers to wrong answers. Of course, usually we won't get 1, usually we won't get 0. The world doesn't work that way. But then we have the different scores. Maybe we do softmax, we check the probabilities, we define some threshold, etc. Okay, so this is for that part. Any questions? Okay, so the constant similarity is basically it's just the dot product after you normalize both of the vectors to the unit length. And this is what we just saw on the earlier example. And we have it also here. We have the two elements, A and B. We just divide it by the normalized form. And then we do the dot product. That's it, very simple. So that means that the real essence eventually is about generating those embeddings, that the created embeddings are ones where cosine similarity will preserve basically what we wanted it to give us. will provide what we wanted it to give us. And why not Euclidean distance? Because in high-dimensional space, all of the distances, they tend to look similar. So Euclidean is noisy. And the second reason, after you do the L2 normalization, then the Euclidean distance and the cosine similarity, they are both, anyway, they are monotonic functions of each other's anyway. So they rank pairs identically. So cosine just has the linear numerical range, which you want to achieve. And if we look here at the geometric reading, so we could have, if it's 0, then we have like same direction. If it's in the cosine of 90, so it's orthogonal, and 180, it's the opposite. Okay, but overall, we have the two encoders that are trained in order to have this match between the pairs of an image and a text, etc. Okay, now the constructive learning, this is the second KD there. So the picture on the left is the high-level intuition. So you have an anchor. Let's say the anchor is an image. And you want to bring the matched caption closer in the embedding space. Okay, so you have whichever embedding you have for the image, you have the caption, you want to bring both of them to be similar. And you also want to push all of the others away because you want to tell them, hey, it should be 0, this should be 1. Get farther from here. So basically, so the code on the right is the actual loss. It's called info NCE. So if we look at the code here, we are getting both of the embeddings and the temperature. So we have the logits calculations, and if the inputs are already normalized, so we just do the dot product, right? This is what we saw before. So in step 1, you compute the similarity matrix between the n image embeddings and the n text embeddings in the batch. You divide this by the temperature. And step 2, what you do, you declare the targets. The if image, which match text is the if text, then this is how the batch was constructed. So the targets are going from 0 to n-1. Now, step 3 is the cross entropy. So you treat each row of the logits as a classification over the n classes, where the correct class is. Okay, so that's it. This is exactly the same form as a softmax classifier, with the classes being the in-batch text embeddings. Now, 2 important consequences. First, the larger batches, it's a harder problem because there are more negatives to discriminate against, and then a stronger signal. Now, CLIP used the batch of 32,000, 32K. And second, this is a symmetric problem. So if we look at image to text, then the text to image works the same way. So CLIP does the average of both of the directions. Okay, so in the aspect of a vision transformer. So for the vision transformer, we have the aspect of the image, let's say 224 by 224. We split it into patches, 32 by 32 patches. Then we do the projections. So from each one of the patch that we had here, it goes to a 768 dimension. And then we add the CLS and the positional embeddings. We have then the self-attention mechanism and eventually the actual output product. So the key intuition here is that a vision transformer, it treats the image as a sequence of visual worlds. Okay, so we had these patches, we had the linear projection of them, right? All of this vector. So these are the visual world, not world, visual worlds that it has for an image. Okay, now each transformer block is the same. It's the same ones that you know from NLP, of course. It's the multi-head self-attention and NLP. And the CLS token is a learned summary vector. So this is what you eventually use for the aspect of the image embedding. And they also released other backends that use the ResNet variants, etc. But the visual transformers are the strongest, at least back then, 21. Okay, any questions about it? Now, the vision transformer trick was to stop trying to invent the vision-specific biases and just reuse, okay, the transformer. So, like we said already, to make the transformer get an image to its input, this is what we described, that we take it, we cut it into the non-overlapping patches. And then we have, for example, for the image that we just said before, so if we take it and divide by 32 on each one of the dimensions, so basically then we are getting 7 by 7. So we have 49 patches. So that image basically is 49 patches, and each patch gets flattened and linearly projected to the 768 dimensions. So then this is the visual token. Okay, and it's very important to understand this part, because this is the basic part here, and shouldn't look at it as something overly complicated, because if, for example, I want to quickly explain to someone what the tokenizer is, we could look at tokenizers not from images. Let's look at ones for LLMs. So this is a tokenizer. I can write here text. We will see the tokens. So hello world. We are studying build on so this is a tokenizer for text. So different words have different tokens. Not necessarily every word gets its own token. We can see here that the LLM, it's 2 tokens. It's the token of the L separately, and the LM separately. By the way, and not every tokenizer is the same. If we look here at different tokenizers, so this is for GPT-5 and 013. Let's look here. Same. It doesn't matter. It doesn't mean that, hey, yes, so the tokenizers are the same. No. We just provided also with a short sentence, right? It doesn't cover all of the vocabulary. By the way, maybe let's check if we look at the token IDs. Let's see if the numbers change. Yes, we see the numbers completely change. So even though the tokens for that specific sentence, the tokens were the same in the aspect of in both of them, each word had its own token, and the LLM had 2 tokens, but the indexes are different because training was different. Even, I mean, for the same vocabulary size, if I will train several times, I may get different ideas. So probably here it's the same, plus, aspect of what's the size, what's the dimensions, what's the vocabulary size, etc. Something that I didn't check in the past, let's see if there's an online vision tokenizer. Looks like it's text only. Possibly. I don't see here something that says upload an image or some demo, but okay. Okay, so once we had these tokens, then we gave it the learnable token, meaning we added the learn positional embeddings. And by the way, this is something very common, right? In the industry, the aspect of the positional embeddings. Okay, and basically note that it's identical to BERT, nothing which is image specific in the encoder past the patch aspect. So this is exactly why this architecture transfers so well from NLP to vision. And this is also how audio models like Whisper work in similar aspects. Okay, so the previous one was the vision transformer that we had here. Now we look at the text transformer. So in the text transformer, we have the caption, then we have the sequence of integers, right? The indexes. Back then, for their paper, they defined here a max length of 77. So you end with your S, for example. Then each one of the tokens that we had, because we have the indexes, it was a mapping, right? It was mapping to the embeddings. So the embedding size here is 512. Anyway, it gets added with the positional embedding, and then same. So basically, if we go back, we add here plus the positional embedding, 12 transformer blocks, and here take end of sentence and project. Okay. So for the text encoder, like we said before, it was the last part of it was equivalent. The first part was the part which was specific for the aspect of text. Okay, that's it overall for this part. And think about it. I think many times you could look at something and you could say, yes, okay, it's understandable, looks simple, etc. But this is also always when you're handed out with the solution. Otherwise, many times, if you're just given with the problems that you're trying to solve, this is a much slower and much more complicated process. So even though we could see things which we could say, okay, simple, meaning we took an image, split it to patches, had this projection, created the embeddings, and all of the rest. But eventually, this is a milestone. And for many of the things, I think eventually it depends, right? But for some of the topics, eventually they look simple, but the value is huge. Plus, no one claims, I think it's really that simple. It's simple once you understand it. Okay, so how CLIP works. So we have the two inputs here. So we have the image, photo of a cat, and we have a text says that this is a photo of a cat. One goes through the image encoder, with whichever backbone was defined for it. Goes through the linear projection, so we have its vector. And same goes for the aspect of the text. So we have both of them. And this is where the loss function comes into action, where in that case, where yes, the labels should have been the same, we would have wanted to have value close to similarity score of 1. Any questions about this part? Okay. Now the important part here aspect is that they're both projected to the same latent space. Therefore, the cosine similarity is relevant then because they are in the same space. Okay, so how did they build that specific data set that they had there? So they had 400 million image and text pairs. Overall, they started from a list here of 500 million high-frequency English Wikipedia queries. Then for each one of the queries, they did scraping. So they brought a pair of the image and text from the public web until they had only 20,000 pairs per query. So the result was that the 400 million pairs covering a much wider visual concept in this aspect versus previous labeled datasets. And again, previous labeled datasets such as ImageNet, etc., people worked very hard in order to do this labeling. So, by the way, if I go back in time to 2021, I think CLIP is one of the reasons that some of the companies disappeared. So many companies whose focus was on the aspect of data labeling or creating the data sets or things that are related to those domains, some of them closed the company. I remember back then one specific company which I always reviewed, and they closed it. Okay. Critical cavity here, they never published their data set. Then this work was reproduced by this LAIOM. And they created OpenClip. So right now you could download, you could experiment with OpenClip. Okay. See, time-wise, we can go on the break now. And let's come back by 55.